Okay, so we've been looking at how to take the derivative. And when we've been taking the derivative, basically what we've been doing is we've been going to say from f of x to f prime of x. Okay, that's what we meant by taking the derivative. But since we said that when you take the derivative, you really create a new function, f prime of x. You started with a function f of x, you took the derivative and you created f prime of x. That's a new function, so why couldn't I just take the derivative of that? And you can. So basically, this first time that we took the derivative, what we're calling the derivative is really the first derivative. Okay? So if we just say the derivative, we often just mean the first derivative. But I could take it again, and if I took the derivative again, I would get what we can write as f double prime of x, known as the second derivative. Okay, and that would be a new function. All right, and so I could even keep going. I could take the derivative again and get f triple prime of x, known as the third derivative. Okay. And this can keep going on. So there's a bunch of things here I want to say. Well, there's certainly lots of new functions, and one of the big things is we're going to talk about later on what does this derivative function say about the original function? What does this second derivative say about the first derivative, and what does it say about the original function? Etc., etc. We're going to want to look at a lot of those ideas. Okay. So the second thing is that there's going to be a lot of notational issues here, because certainly I don't know how many primes I'm going to want to end up putting there as I get to the 5th, 6th, 8th, 10th, 20th derivative, and how do I deal with that? Okay, so let's get into that first. Notationally, how do we write these things? So what I've set up here is a little grid where we can talk about whether we're looking at the original function, the first derivative, the second derivative, etc. And then how we're calling it. Are we calling it y, like in these cases, or are we calling it f of x, like in these cases? And all the different types of notation that we have associated with the derivative, like the prime and the Leibniz. All right, so let's just go through a bunch of different varieties here. So the first derivative, if I'm just using prime notation and I'm calling the function y, could just be y prime. Or I could say dy dx if I'm using the Leibniz. Okay, if it's called f of x, I could do f prime or f prime of x, or I could use the d dx of f of x. Okay. Now I go to the second derivative. If I called it y, the first one was y prime, and then it could be y double prime. All right, so now how do I deal with the Leibniz notation here? So what you do is you're thinking of basically the operation as d dx, which you've done twice. So to indicate that, we actually use a superscript, almost like a power, but it's not really the power. But it's d dx, or d squared dx squared is what we usually say, of y. Okay? So we're indicating right here how many derivatives we're taking. All right. The prime, a little more straightforward at first, just f double prime of x for the second derivative. And over here, still like before, d squared dx squared of f of x. Okay. Third derivative, y triple prime, d cubed dx cubed y, f triple prime of x, that's a third one there, or d cubed dx cubed of f of x. Okay, So far, so good. Now, when we go to the fourth derivative, we don't want to keep writing the slash forever. So at this point, we usually switch. And we usually switch and we put the derivative number in parentheses as a superscript, telling us it's not a power, it's the fourth derivative. Okay, so that's where that notation has to change. The Leibniz notation does not have to change here. We could do d to the fourth, x to the fourth, y. And over here again, 4 in parentheses to indicate derivative of x, and d to the fourth, dx to the fourth of f of x. Okay, so you see there are benefits and drawbacks to each notation, and that's why I like to use both. All right. So in general, for the nth derivative, we would have y, the nth derivative there, dn x to the n y, okay, f nth derivative x, and dn x dx to the n f of x. Okay. So now we also could talk about this in relation to motion. So when we start talking about derivatives and instantaneous rate of change, I made the connection to movement, and that if you had a position function that was, say, s of t, which is often for our position function, okay, and then if you wanted to talk about its instantaneous rate of change, that would be the velocity. Okay, so the velocity, v of t, is just the first derivative of the position. Okay, so then the acceleration, which is the change in velocity, is now a of t, which is the first derivative of velocity, or the second derivative of position. So now we're seeing how they relate to each other. Okay, so we have this chain of derivatives and different meanings for them. If you're interested, there is a change of acceleration that would be called jerk. Interestingly enough, but not surprisingly, because that's the jerk you feel when you change acceleration. So when you're in an elevator and the elevator is going up or down, you don't usually feel the acceleration. What you feel when the elevator jerks is actually a change in acceleration. That's what you're feeling, is that jerk. Okay, so let's look at some examples of how higher order derivatives would work and some interesting things that we can find. All right, find the third derivative of each function. Okay, well, we just have to keep going through the derivatives. If we have f prime equals, okay, 3x to the fifth, that comes down, multiplies to 3, so 15x to the fourth. Then we just do it again. F double prime, 4 times 15, 60x to the third. And then the third derivative of x would be 180x squared. And what you might be noticing, although we've stopped at the third derivative, is that you keep taking derivatives here. The fourth derivative would be 360x. The fifth derivative would be 360. The sixth derivative would be 0. And every other derivative after that would be 0. So basically what you're saying is that if you start with a polynomial and take enough derivatives, you'll eventually get to 0 and it'll be 0 forever. Interesting point. Okay, let's take a look at this other one. X squared plus cosine x. Again, first derivative, the x squared becomes 2x. So I have plus the derivative of cosine x, but that's minus sine x. All right, go to the second derivative. Derivative of 2x is just 2. Minus derivative of sine x is cosine x. And then the third derivative of 2 is 0, so that's gone. Then I have minus cosine x becomes minus sine x, so this becomes positive. So I will just get rid of it and sine x. Okay? So I end up with the third derivative there being sine x. Another interesting thing you might be thinking about, if I take the derivative of sine x, I go to cosine x. I take the derivative of cosine, I go to minus sine x. I take the derivative of minus sine x, I would actually go to minus cosine x. And then if I took the derivative of minus cosine x, I would actually go back to sine x. So there's something interesting. It becomes a loop that goes on forever. Okay? So you have this little for cycle of derivatives of sine and cosine with negatives in front. Another interesting fact. Okay.